All right, so this is the second half of the lecture for topic 2 for week 7. We will continue on where we left off, looking at acceleration of a simple harmonic oscillator. So this is the lecture we're looking at. We're just going to go straight to slide 20, number 21. It's the 22nd one because of the title slide. Right, acceleration and simple harmonic motion. We've already met velocity. We figured out the equation of motion x as a function of time. We saw that the velocity was going to be the derivative of that with respect to time, the slope of the position time graph. And that gave us negative a omega sine omega t plus phi naught. Similarly, the acceleration is the time derivative of the velocity. It's the slope of the velocity time graph. Hopefully we all remember those basic relationships. Do refresh yourselves on them if you're not confident. But the acceleration comes out to be, again, we've got the omega t inside the cosine, so we have to bring another factor of omega out the front. And then, within the sine term, the sine then goes into cosine, the negative stays there, so we end up with negative a omega squared cosine of omega t plus phi naught. Now we have a maximum acceleration, and that is going to be a times omega squared. Again, feel free to check the units, right? I ask you to do that with the velocity graph. Make sure that it makes sense. What we've got out should be an acceleration. Make sure it is. So that's our maximum acceleration, and then it oscillates between that and the equal and opposite negative maximum, negative a omega squared. So it just cycles between that. Again, the cycle will occur at the same rate as the velocity and position cycle. So just comparing all three graphs at the same time. The top blue graph is the position versus time graph. The middle red graph is the velocity time graph. And the lowest green graph is acceleration time. So you can see that they all look very similar in that they've all got the same period of motion. But what you'll see is that none of them are at the same position, right? None of them are identical. They're all slightly shifted. So as we talked about with velocity versus time, when the position is maximum, velocity is 0, that's where the object is turning around. And for it to turn around, for it to go from a negative velocity to a positive one or vice versa, it must briefly, just instantaneously, have a velocity of 0. So at those points in time, we've got maximum displacement and velocity being 0. But in order for it to not remain at velocity 0, it must have an acceleration at that instant. And if we look at the acceleration graph, we indeed see that that's when the biggest acceleration is occurring. And if you think back to the restoring force, the restoration force, that was proportional to the displacement. And since this instant is where we've got maximum displacement, it makes sense we'd have the maximum restoration force. And since force is equal to mass times acceleration, the maximum restoration force should give us the maximum acceleration. So that's what we see. When x is largest, the acceleration is largest. But importantly, the acceleration is in the opposite direction. So if our position is positive, the acceleration is going to be negative, pulling us back towards that center position, that equilibrium position. So hopefully, just thinking about that, take a bit of time to look at these graphs and really get to grips with what they're representing. Make sure you fully understand simple harmonic motion and what the velocity, position, and acceleration are all doing with respect to time and how they relate to each other. You want to be confident in interpreting those graphs. So let's continue down this train of thought a little bit and look at our acceleration versus position. Our acceleration was negative a omega squared cos of omega t plus phi naught. And our position was a times cos of omega t plus phi naught. The cosine term is the same, the a is the same. The only difference is we've got a negative omega squared for our acceleration that we didn't have for our position. So that means that our acceleration as a function of time is just negative omega squared times our position as a function of time. So hopefully you can follow that math. Right? We've identified the parts of xt that are in at, and the only thing we have to add to turn x of time into acceleration of time is negative omega squared out the front. So that's the only thing we have to change. If the object undergoing simple harmonic motion has a mass m, then the force has to be ma, or m times omega squared x over x as a function of t, because we just saw that a was negative omega squared x as a function of t. So if we look at that, we've got f equals this negative m omega squared times x. Right, so choose any instantaneous time, any t value at all, and you see that f is equal to negative m omega squared times x. But we already know for a mass on a spring, right, in the case of a spring system, that f is equal to negative kx. So if we've got negative kx is equal to negative m omega squared x, then that means that k is equal to m omega squared. And so using that, that relationship, we get out that the angular frequency of a mass on a spring is equal to the square root of k over m, the square root of the spring constant over the mass that's being oscillated. Right, so that's how we get out that relationship. Sorry, it's another way to get out that relationship for omega. So we've already met omega being square root k over m. We already saw that, but now we can see that this way as well. Energy. We're now going to talk briefly about energy. We all hopefully remember conservation of energy. An object undergoing SHM will have, if it's due to a spring, then it'll be kinetic and potential energy. It'll always be kinetic and potential if it's undergoing SHM. In the case of a spring, it'll be spring potential energy and kinetic energy. So just think a moment about the different positions the mass can be in during SHM. Sorry, just distracted myself with a notification that came up on my screen. When we've got a maximum displacement, the velocity is briefly zero. We just talked about this. The velocity was traveling away from equilibrium, now back towards it, has to go through zero briefly, and the same at the other end. So we've got this brief zero velocity. That means there's no kinetic energy. So at maximum displacement, all the energy is in the potential energy. At zero displacement, the spring is completely unstretched, then therefore there's no potential energy. If the spring hasn't been stretched, there can't be any potential energy in it. So all the energy has to be kinetic, and of course that makes sense because we know that's when the velocity is highest as well, as it passes that equilibrium position. So at that moment, at that instant, it's all kinetic energy. What we see is that the energy has to oscillate. At the maximum displacement, it's all potential. At the zero displacement, it's all kinetic, and it travels, it converts from one to the other. So it's all potential, converts into all kinetic, converts into all potential again, all kinetic, all potential, all kinetic, and so on and so forth. So that just repeats. But the important point is that it is doing that at twice the rate, twice the frequency of the oscillator itself. Because the potential energy is positive regardless of which end you're at, and the kinetic energy is positive regardless of which direction you're traveling in, it means that we always have positive energies involved. And so the energy is positive here, maximum potential, positive maximum kinetic, and then positive maximum potential again. So it's already done a full oscillation. It's gone from all potential to all kinetic, back to all potential. But in that time, the oscillator itself has only done half an oscillation because it's now at the other end from where it started. So what we find is that the energy is actually oscillating back and forth twice as frequently as the object itself is physically oscillating back and forth. We've got a couple of equations. We know kinetic energy is half mv squared. That means the maximum kinetic energy is a half m times v max squared. And of course, we know that the energy is going to be conserved. So that is equal to the maximum potential energy. And from spring constants from Hooke's law, you should hopefully recall that the potential energy in a spring is a half kx squared. And in this case, x max for our maximum potential, which is A, our amplitude. So we get that the potential energy is a half ka squared. And so that just gives us this equations down the bottom. We have another way of determining the maximum velocity. So we've already seen that. We've seen the maximum velocity was a omega just from our derivative of the position function gave us our velocity function, and we saw that a omega was going to be the maximum velocity. But we can get that this way as well by just thinking about the energies. If the half mv squared is going to be equal to half ka squared, then we can just rearrange those to solve for the velocity maximum. and we get A omega, or A square root K over M, but we already saw that was omega. So it's just another way to get there, but the point here is just to be thinking about these energies. So if we've got a closed system, right, if our system of whatever is oscillating has no forces being applied to it, it's not losing or gaining any energy in any way, then that means that the energy has to be conserved, and because it's SHM, it's going to sit there and oscillate back and forth between the two. So you should always understand where the energy is. You should be able to look at a snapshot of a system and know where the energy is in it. To help visualize that even more, we've got a graph. This is still that same time frame of all my graphs that I've had in this lecture of going from 0 up to 3 times the period. We've got a maximum energy E, and we've got the kinetic and potential energies oscillating back and forth. And you'll see that in this case, the potential starts at maximum. So that means we've got no phase constant. And the kinetic starts at 0. So that's indicating that the object is starting at rest. And then as it's released, as the time progresses, the potential energy decreases down to 0 as the object approaches its equilibrium position. As it does so, it is all converted into kinetic. And so when when potential goes to 0, kinetic goes to maximum, and then they swap over, it oscillates again. Right? And so you'll see that that just oscillates. But as I said, that oscillates twice as quickly as we saw for the position, velocity, and acceleration. So the oscillations of the system are at some frequency, the oscillations of the energy are at twice that frequency. It happens twice as many times per second. So we're going to finish this lecture by thinking about a simple pendulum. So far we've been talking about a spring mass system, it's a very simple one to do because the motion is just linear. It's just along a straight line. That's all we have for the motion. It's very easy to consider. A pendulum is slightly more complicated because we've actually now got angles. We've got a fixed length that rotates through a small displacement and then rotates back the other way. So we've got to take a little bit of time to think about the maths of this scenario. If we have a pendulum of length L with a mass m on the end of it that's been displaced by an angle theta, we have 2 forces. Right? So we only had one in the spring mass system. We just had the spring force, the restoring force of the spring. Now with the pendulum, we've got 2 forces. We've got tension directly towards the pivot point, and we've got gravity vertically downwards. If we need to decompose the weight force, right, we need to choose a frame of reference that makes sense for our decomposition. What we end up seeing is that the tension is going to be equal and opposite to some component of the weight force. So let's choose that as our frame of reference that we want to break it down into, that we want to decompose into. So we've called it FWR, which is the weight force radial, pointing in line with the center of our motion, which is our pivot point. So directly opposite to the tension. And then also the weight force tangential, the sub T, little subscript T there. That's the one that's pointing along the path of the pendulum bob, and that's the one that we're responsible for actually moving that pendulum bob back towards the center. The one that's pointing away from the tension, that just balances the tension. That means that the bob stays at the end of the string. It can't go up the string, and it can't go further than the string will allow it. So they just balance. And then the tangential component pulls the bob back towards its equilibrium position. So we're going to decompose the weight of bob into those 2 components, but of course we only care about the tangential one, and as you can hopefully see, just some basic trigonometry gives us that the tangential component of the force is negative mg times sine theta. We've put the negative in there just to indicate the force is opposite to the displacement. So if we define where that pendulum bob is positioned as being positive, then the force is negative because it's pulling it back towards 0. So the negative is in there because it's a restoring force, as we saw with spring constants. We also know that the circumference of a circle is 2 pi r. So if you, sorry, I'll go back a slide a second. If you take this path that the pendulum bob is traveling along, and you continued it all the way around, you'd see that we get a big circle of length, of circumference 2 pi L, where L is the length of the string. Right? If L is the length of that string, then the path that the pendulum would take if it did a full circle would be 2 pi L. But of course, the bob hasn't done a full circle. What it has done is it's traveled some little amount along that pathway. Right? And since a full circle is 2 pi radians, if it travels theta radians, then the fraction of the circumference that the bob has traveled is theta over 2 pi. So that means we can take our circumference, multiply it by the fraction of that circumference it's done, which is theta over 2 pi, and we see that the path length the pendulum has actually traveled is theta L. All right, so going back a slide again, sorry, I'll jump back and forth a bit on this one just because the diagram is useful. So we've gone through some angle theta. This path length here is just L times that theta. That gives us the length of this path from our equilibrium position here up to this position where it actually is. So that is our path length. Now there is a thing called the small angle approximation, and that tells us that for small enough angles we can use the approximation that sine theta equals theta. I'm going to jump over to the document camera because I just want to take a second to convince you of that one. So if you've got a sine curve, hopefully you're all familiar, sine curves go up and then back down. And so what the argument is, remember it gets to 1 up here. I haven't drawn this very well to convince you actually. Let me try that again. I'll draw an extra couple of lines in here. So here's our y, here's our x, and sine tells us that when we get to 1, when we get to pi here, we get to 1 here. Right. And obviously it continues on. But the important thing is that if you draw a straight line, so remember pi is 3.1, so about a third of that. So if we go at 1 there and go up to here, and you draw a straight line there, you can see that they start very similar. So if you zoom in on that little bit of the graph, for very small angles of x, in this case x, in our pendulum case it's theta, but for very small angles they're actually going to be very close to the same. So what that lets us do is it says that if our angle theta is small enough, instead of sine theta we can just write theta. It's going to be very close. What counts as small enough? Well, that depends on your precision. If you want to be very precise, then it has to be a very, very small angle. If you only care about a couple of decimal places, you can go to a slightly larger angle because it will be within 2 decimal places for longer than it will be, say you wanted 5 decimal places, you'd have to be a very small theta, and so on. So the what counts as small enough is only answered by what is your precision. Right, so in our case, because we're only ever going to be doing a few significant figures, generally we can allow reasonable angles of theta. If you want to get very precise, you're going to need to have, go to restrict it to smaller angles of theta. So that's the small angle approximation, and that means that the component we just found, the tangential component of our weight force that was negative mg sine theta, we can now write as just negative mg theta. We don't have to have the sine term in there. That means that our acceleration, because F equals ma, that means our acceleration is negative g theta. And if we look at the path length that we just considered up here, we see that the theta is s over L, path length over L. So we get that negative g theta is equal to negative g over L s. Compare that, CF is just Latin for confer, which is means compare. So compare that with the acceleration from our mass on a spring, which was omega squared x, where x was our linear displacement. Now s is our travel distance along the path of motion of the bob. It's the same format, right? We've got a is equal to something times s versus a is equal to something times x. So that means that our acceleration there can tell us the angular frequency of a pendulum now. So we get angular frequency of the pendulum is the square root of gravity over the length of the pendulum. And this is something that most people learn fairly early on in science, is that the period of a pendulum, right, so period being 2 pi over omega, so 2 pi square root L over G, we've flipped up omega from G over L to L over G. Period there is independent of mass. Right? It's independent of mass, it's independent of amplitude. It doesn't matter how big you actually do it. Again, you need to remain within that small angle approximation, so it won't work if you pull it all the way up to halfway. Right? So you can't pull the pendulum heaps far up, but as long as you keep it within small enough angles that your approximation is within your precision, then it means that the amplitude is irrelevant, the mass is always irrelevant, and we get the period depends only on the length and gravity. So that is the period of a pendulum. And of course, we can put all of that information into the equation of motion for our pendulum. This time, you have a choice of doing it in terms of the path length s, which was that distance along the path the bob travels, or in terms of that angle theta from straight down, how far has it gone in terms of an angular displacement. There we've written it as an angular displacement, so theta at time t is equal to theta max, so the maximum displacement, which is like the amplitude, times the cosine of omega t plus phi naught. That's just a different way of writing phi, since we've got a different equation. We've written it a different way. But the equation itself takes the exact same form. We've got a maximum displacement, in this case angular versus a for linear displacement, cosine of our angular frequency times time, plus a phase constant to allow for those initial conditions. So exactly the same format, and all the other analyses would then be exactly the same, because we've got that same equation of motion to start with. So we'd get the same idea no matter which aspect of the system you looked at. You take the velocity or the acceleration, we're still going to get those same maximum velocity and accelerations out. If you look at the energy, you're still going to get that same relationship. When the bob is straight down, at its equilibrium position, zero angular displacement, all the energy will be kinetic energy as the bob is swinging past the center, no potential at all. As it swings along, it goes up slightly. As it goes up, it's now gaining gravitational potential energy. By the time it stops moving, as it's turning around, it's got no kinetic energy. It's all potential energy or gravity or gravitational potential energy. Then it all converts again as it swings back. So we get the exact same results, just with a slightly different system. So that is all of the theory for this lecture, for lecture 7.2. A brief summary obviously pays to go back and read through everything, but there is a brief summary there for your perusal. And as usual, there will be a few questions to follow this. I will do that in a separate video. So for now, I'll see you later.